Okay, science time today. We're going to talk about magnets. We're going to call it magnets, but it's going to be titled on YouTube Basics of Magnetism or something like that, because we're only going to talk about some very, very basic things.
Mr. Kime, do you ever think about if other schools watch your YouTube videos?
Yeah, I do think that, and they don't. So that's convenient. Yeah. Let's. What is a magnet? Is a magnet magic?
Yes. Very magnet.
No.
Scientific
It's science. Yeah. If you there such a thing as magic? I don't know. I've heard magic described as something that works that you don't understand. And that's okay. I guess that's okay to describe magic that way. But the point of magnetism is that we have some object that exerts a non-contact force. It's a non-contact force, meaning what? Remind yourself, meaning what? Yeah, it does not have to be touching. And then here I'm going to try to draw a little paperclip. That's a pretty good paperclip. This magnet is going to attract this paperclip with a non-contact force. What if now? And you know that magnets have poles, right? We'll call this the North Pole, and we'll call this the South Pole. That's usually how we designate the poles of a magnet. We'll call that the North Pole and that the South Pole. What if we bring, instead of a paperclip, which is attracted to the magnet, what if we now bring into contact, I'm going to draw another one, sorry, instead of erasing that one. Here we have a magnet that is, this is the North Pole, this is the South Pole. What if we have another magnet now, and this is the South Pole, and this is the North Pole? What kind of force is going to happen between these?
Contact.
No, not right away. What kind of force is that going to do? No, try again.
They're going to attract each other.
Okay, we have two different differences in opinion. One person says they're going to pull each other together. The other person says they're going to push each other apart. Which is right and why? JJ, what do you think?
Because...
Well, which one?
Oh, well, the North and the South are going to pull each other towards.
Okay, why?
Because they're opposite poles and then...
The evidence that you should have found in your lab suggests that opposite poles attract. Let's write that down real quick. Opposite poles attract. Opposite poles attract. What if we now have it instead like this? North and south, and this one is also north and south. What force is that? Yeah. Same or similar poles. What do we call that? What verb?
Same.
Yes, same poles. What verb should I use here?
They repel.
Repel. Unlike gravity, remember gravity? Gravity is always attractive. In gravity, all objects with mass attract all other massive objects in the universe. Remember that about gravity? But unlike gravity, there's no repulsive force in gravity. Nothing is pushing each other away in gravity. Everything attracts everything. But in magnetism, there is a repulsive force. It's what we call a polar force. It has poles, and those poles attract when they're opposite, and they repel when they're the same. What causes magnetism?
Magnetic domain.
Okay, magnetic domain. So if we look microscopically at this magnet here, I pointed out a really weird piece of
Arrows pointing.
yeah, they won't have arrows pointing there, but we represent it as there'll be regions of this magnet that are kind of like, they're kind of tessellated, but they're also kind of randomized, chaotic shaped. It doesn't have to be right down the middle like I have drawn it. They're random areas of a magnet that within each of those random areas of a magnet, there is some kind of polarity. So maybe each one of these, if we're looking at, let's pretend we're actually looking at this part here, closer to the North Pole, I mean. We're going to show that most of these are lined up north and south. This one, maybe it's a little bit off center of north and south, but all of these, on average, are lined up like little itty bitty miniature magnets. Every single one of these acts like a little miniature itty bitty magnet. What if I cut this magnet in half? Does it still have a north and a south pole, or is it now just all north pole? Which is it? It's still north and south. There is no such thing, or at least no one has ever discovered, there's no evidence of such a thing as a magnetic, what we call a monopole. There's no such thing as a magnet that only has one pole. in fact, there are a lot of hypotheses about how if a magnetic monopole ever did come into existence, it would ruin the universe. And you can look up these things. There are mathematical proofs about how perhaps the end of the universe could come to pass because of the creation of a magnetic monopole. But as far as we know, that can't happen. And an idiot, a stupid person would just say, well, I'll just cut a magnet in half and then it'll all be North Pole. And just because the magnet is painted North Pole and South Pole and you cut it in half, now that you have only the side painted North Pole does not mean this is just the North Pole of a magnet. It still has a South Pole too, it's just not painted that way anymore. Because every single one of these domains has its own North and South Pole. And the magnet behaves like an average of those domains. And more to the point, each of these domains is made of what? On the submicroscopic level. Yeah, they're all made of atoms. And these atoms, which in this case probably iron, the three elements that are most commonly able to be magnetized are iron, cobalt, and nickel right here in a group, and that's not a coincidence. But iron, cobalt, and nickel are the most common permanent magnets. But anyway, they're all made of atoms, and these are probably iron atoms. And the electrons that spin around the atom, you have some understanding about the arrangement of electrons, right? No. Have you ever heard the word electron before?
Yes.
Have you heard the word atom before? Yeah, what else is a atom made up besides electrons? Neutrons and protons. But it's because of the spin of the electrons. Each electron has its own little quantum property that we call spin, which we're not really going to get into, but the spin of the electrons causes this magnetic field. And so maybe the electrons with that particular spin are all lined up one way, and that causes this domain to be lined up that way, and then that causes this magnet to be lined up that way. So it's because of the spin of the electrons, and that's why not every substance is magnetic. Could I make this this marker into a magnet? Probably not. Maybe with some super high technology I could cause more of the electrons to spin in one particular way, but under normal circumstances and with normal things that normal people have, no, I can't make this magnetic. Only some materials even have the capability of being magnetic. When someone in their lab, I'm going to move over here now, when someone in their lab had a magnet, and they attracted a little paperclip to it, is the paperclip magnetic?
Yes.
Well, yeah, at this time it is. The paperclip at this time is what we call a temporary magnet. Whereas this we sometimes call a permanent magnet. That's not, well, for one thing, nothing's permanent, right? Everything decays. Everything eventually becomes dust. Nothing survives. The universe's trend is towards destruction and entropy. But that's a little bit bleak and not really what we're talking about. We still call it a permanent magnet because it still has this magnetic field even when it's not in the influence of another magnetic field. A temporary magnet only has its own magnetic field when it's inside of another magnetic field. When have we heard about fields before?
In our exploration.
Okay. But also in another exploration from before. What else? What else was exerting a field? What is a field? What do I mean by field? Football. I'm talking about football. I'm always talking about football. No, we're not talking about football in this case, although obviously the word is the same. What is it? Okay, let's define field on a very basic human level. What does a field mean? The football field, the wheat field, the field of medicine, a magnetic field. What do those things all mean? An area, yeah. So a field is kind of like an area, kind of. I'm going to put a little squiggly equal sign. A field is kind of like an area in either a metaphorical sense, like the area of medicine, or in a literal sense, like the area of the football field. But also, it's this area around a magnet where the magnetic force is exerted. And do we see these magnetic field lines?
No.
Not normally. No, not normally. We don't see these magnetic field lines. It's invisible. It's a force field. That's where that phrase comes from. It's a field of forces. And a magnet can interact with this field and exert its own magnetic force, or another thing that is a temporary magnet can interact with this field and be attracted to the magnet in a non-contact way. What else did we say exerts a field force? We had one of these back in the past too. Here's Earth. This is supposed to be Earth. Gravity. Gravity has a force field around it the Earth has a force field around it of gravity. Remember, the gravitational force is only attractive. So even something here, a cat maybe, this is a gigantic cat. The cat is the size of freaking Sweden. But this gigantic cat is gravitationally attracted to planet Earth. Non-contact, right? It's a field. There's a force field, and get this. This is the main thing I want to get at, and I really like this idea. This force field, the gravitational force field of this object and of all objects, and the magnetic force field of this magnet and all other magnets, and the electric force field, which actually the magnetic and electric force field are one, called the electromagnetic force field, but that attracts the protons and neutrons together and causes things like electricity. Those fields actually permeate the entire universe. When you get right down to the subatomic level or the subatomic level, on the quantum level, every particle, like electrons and the iron atoms, the nuclei, all of these are really just excitations. They're waves in a field. Everything is all just waves in a field. To us, it seems like matter, but in reality, on the quantum level, everything is just waves in a field. And that is kind of spooky, but that is the way that the math and the science tell us that it is. That all of this permeates the entire universe. We know that a little Lucas Allen here on Earth causes, Lucas is the size of Guatemala, but a little Lucas Allen here is exerting a gravitational force on Uranus, isn't he? It's minuscule. It is absolutely almost incomprehensibly small, but he is exerting a gravitational force on that. Everything is connected. Same thing with the magnet. Every magnet that exists or has ever existed is exerting a force on another magnet. It's all force field. It permeates the universe, and these non-contact forces are manifestations, are excitations in the force field. There are other kinds of magnets, and I don't mean different materials magnets can be made out of, like your alnico or your neodymium boron magnet or whatever. Those different kinds of things that magnets can be made out of. There are different types of magnets, but there are also different categories of magnets, such as temporary magnet, permanent magnet. There's things can be diamagnetic or paramagnetic, and you can look those up later. Yes?
So when you were talking about like how different gravitational forces, big or small, can be exerted on other magnets, I kind of thought of how the moon would create tides on Earth.
Yeah, exactly. So if here instead of a cat, we have a moon, the moon certainly does exert a gravitational force back on Earth, and that causes the tides. Just like if we have this magnet, it can attract a whole slew of paper clips to it, and those paper clips can attract other paper clips. And if we have this magnet, and if it's in a bigger magnetic force field, there's a bigger magnet over here, that magnet itself will be attracted to it. And that's that's an approximation of the tidal forces exerted by gravity. Do you have other questions about magnets in general? I want to ask you a couple of questions. What happens when similar poles of a magnet come into contact, or not necessarily contact, but come near each other? Similar poles repel, opposite poles attract, and all of the magnetic force is because of this idea of magnetic domains, and at its core, it's because of electron spin in magnets. Do you have questions? What are your questions?
Why is the sky blue?
Why is the sky blue, Tommy? Does anyone know?
I don't know. Maybe.
You can get a real pedantic answer out of someone. It won't be me. You can get a real pedantic answer about something like Rayleigh scattering, which is a real thing. But what the real reason is that oxygen is blue. The oxygen is the color blue. So when you see through oxygen, you see blue, just like water is blue.
What about actually?
Yeah, clouds are water.
Yeah, we're looking like a.
Bye.